Alrighty, so class. Victor?
Yes.
Yes, loud and clear. Thank you. Appreciate it. All right, so we actually have a really short lesson. I got 2 examples to go over, and only thing for the homework is the AP problems. So, because that's the type of problems you're going to have for these. So, uninhibited and inhibited growth and decay models. And these actually go along with something that we did with derivatives the first time. So, going through, solving differential equation involving uninhibited growth and decay. So the derivative dA dt is equal to k, which is whatever the number is, which is going to be the the factor that it's going to be going up or down by, and times whatever the a is with the population. Okay, respect to time itself. Okay, k cannot be 0. So if k is greater than 0, it's a growth. K is less than 0, which negative numbers, okay, it's going to be a decay. So I'm going to start by writing it dA dt is equal to k times a. And here's the step-by-step on actually changing it from the derivative model. Okay, thank you. The derivative model all the way into the formula. So we don't have to know how to do this all the way down, but it is good because we start off with the derivative. We separate the variables, which we put all the dt over here and all the a over here. So dA over a, so that means I'm going to have 1 over a dA. That's what I have on this side, on the left side. And on the right side, it was the k times dt, k dt. And to undo that derivative, after we separate this, that's what we have here. We have the a's on the left and the t's on the right. So for this right here, when we take the integration to undo the derivative, 1 over a is ln absolute value a is equal to kt plus c. Ln a, undo that right there for a is greater than 0. So a is the same as a sub naught when t is equal to 0. So, and then a sub naught, ln a sub naught is equal to c. So as we go and put this together, we work it out, do a little math, okay, and we end up with a is equal to a sub naught, which is my initial about, times e raised to the kt. Now, do I need to know all the steps all the way down, memorize it? No. Do I need to know the formula down here on the bottom? Yes. So, growth, okay, so uninhibited growth or decay means, what's the word inhibited mean? Okay, good, yeah. It's restricted to something, right? So, now, one thing that it comes up a lot, they talk about news and all kinds of stuff, it's the world population. Is that inhibited or uninhibited growth? Why is it inhibited? Very good, yeah. There is a limited amount of resources for what we have in our environment. So what the resource that we currently have, we have a limited amount, so our population growth is inhibited. Uninhibited would mean that it can go on forever and keep going. As we start colonizing other planets, there we go. Then we're going to find more resources. Assume colony of bacteria grows at the rate proportional to the number of bacteria present. The number of bacteria doubles in 5 hours. How long would it take for the number of bacteria to triple? Okay, so I know that my time t, so it should be from its start, it's whatever amount, So I know it would double. So let's say if I put my initial amount here, e to the kt, my output should be what? What does it say? It will in. Okay, so what information does that give me? Do I have one of my variables here? My kt, right? Kinda. I got my t though, right? I got my t. And what else do I have? It will do what? It will double. So it will double what? My initial amount. So it's going to double my initial amount. So I'm going to get 2a is equal to a sub naught e to the k, and then that's going to be 5. Okay, so do a little bit of math. Because my initial amount's going to double, so that means, let's do this, a0, my initial amount, so it's going to be 2 is equal to e to the k times 5. What else can I do? How do I undo an e? Because my variable's up here, isn't it? L on both sides. So I'd say ln of 2 is equal to 5k. So I have a value for k, right? All right, and now from there, how long will it take? So what am I looking for now? Reading through the question, what am I looking for? Time. I look for time, right? So I now have a value for k. I have a value for my a sub naught, which is whatever my initial amount is. How long will it take for the number of the bacterial to triple? So what information do I have now?
You're solving for 3a.
3a, very good. So it's going to be a 3a is equal to a sub naught, which whatever my initial is, e to the k, which I'm just going to put k as k for right now until it's time to plug in a calculator. Okay, because I don't want to keep writing that over. This is my k value. K t. Divide both sides by my initial value, which is going to be, so 3 is equal to e k t ln is equal to k t divided by k. So ln 3 divided by my k value, which is going to be over here. And then I'm going to plug this in the calculator because I'm not going to be so bold as to try and do that by hand. So as that's loading, I'm going to clean up my math a little bit. There we go. Because I'm dividing by ln 2 over 5, right? So can I just rewrite that as 5 ln 2 over ln 3? Yeah. Okay, there we go. So now I'm going to plug that in. So 5 ln 2 ln 3. did I have that backwards? Should be, yeah, it should be ln3. I'm sorry, over 2. Yeah, I put it in the wrong spot. Sorry. So ln3, ln2. There you go. Now, in calculus, how far do we round? 3 decimal places. So my answer is going to be 7.925. What are my units? What did we solve for? We solved for time. We solved for time. So when time in this problem is hours.
How do you get rid of how do you get rid of A with A sub naught?
Okay, so A sub naught is my initial amount. That output A is just whatever I end up with over here, right? And so 3 times, it's basically 3 times A sub naught. So it's going to be that value. Whatever value I have here, it's just 3 times that.
Then what's the point of all the E if it's just going to be times 3?
Okay, because you might have missed this, where we went back to and it said we're trying to get the bacteria to triple.
So you know how much it doubled?
I know, but I don't get how you got rid of A with A sub naught.
Yeah, because then, I don't know. When A,
Okay, you guys missed the. Yeah.
That don't make any sense either.
Okay. See this right here? This is a formula.
Yeah.
That's a formula. A sub naught is my initial amount. Okay? Whatever I start with here, it gets multiplied by E raised to the KT. And after I do that, A is my output.
Yeah.
It's whatever the amount is. So A sub naught is the initial amount. A by itself is just my end amount.
So it's going to be a different amount, right?
It's going to be a different amount.
So how can you get rid of A?
Okay, so now if you start with $5 right now and I say, hey, triplet, how would you get that? Times by 3, right?
Yeah.
How'd you know it's times it by 3?
Because you said the triplet.
You said a triplet, so it's 3 times your initial amount gave you your output. So your initial in this conversation is 5, right? Your A, your output was 15.
Yeah.
That's where we get that. So right now we're not working with any value. We're not working with a initial value. We're working with the formula here to try and solve for it algebraically. So we're using our formula to go in, plug in, found our K, which is our growth or decay. And then from there we plug it in to actually get the value to figure out the time it's going to take for that.
So basically, you're only able to do this because you're trying to figure out the time.
Yes, because it just says it's 3 times whatever it is. If I had a different value here, there was 5 here, then it would be 5 times all this, and then it would come out with something else over here. So when we're dealing with an initial amount and an actual output amount, that's different. This is more theoretical just because I don't have an initial amount. I just know that my output is going to be 3 times as much. I think what's tripping you up is the fact that we don't have any amount here, right? We're just trying to solve for our T and our K.
It's true because then, like, when it's A initial and A regular.
Sub naught, yeah. A sub naught, and then A, whatever my A is end result.
Kind of indicate that 2 different values. So it's like
Yeah. In this case right here, it's going to be.
Same value.
Yeah, all it is, it's going to be 3 times whatever that value is.
It's just weird to look at, you know, because you're so used to.
9? Yeah. So let's go here. Radioactive substance, rate of growth and decay is proportional to the amount of substance present at a given time t. If A is equal to A of t, represent the amount of radioactive substance at time t, where K is less than 0, depends on radioactive substance. The half-life of radioactive substance is the time required it takes for the half-life substance to decay. For how long it takes for there to equal how much? Half. That's important. Okay, that's important. Half-life means, you ready, Blade? How much of A is going to be left if I'm looking for the half-life? Half of A, right? There you go. Should be half of A. Skeletal animals found in an archaeological dig contains 20% of the original amount of carbon-14. Half-life of carbon-14 is 5,730 years. How long ago did the animal die? Okay. I know that half-life means half of it should be there, right? I know that whatever my A sub naught is, I should end up with how much? 1/2 A. Yeah? Blade, does that make sense?
I'm trying to figure it out right now.
Okay. Do you want me to write A sub naught?
No, I'm just trying to. I'll follow along.
So whatever my initial is, my A, I should get in a half-life half of whatever I had. Now, continue the formula. E, K. Do I have a T value? Yeah, there we go. So it's going to be 5730. All right, divide both sides by A sub naught, so I should get 1/2, right? I ln both sides, but here, I'm not going to skip a step. Ln of, let's see. Now, we can rewrite ln 1/2. That's going to help us out here. What can I rewrite that as? Ln. Perfect. Because it is a fraction, right? So it's going to be ln1 minus ln2 is equal to 5730K. Yeah, I'm going to divide by that, but before I get too far, what's ln1? 0. ln of 1 is always 0. And that's one of those things that it's going to make your math a whole lot easier because I divide both sides by 5730. And so all that is going to give me my K value.
What is the K value?
K value is its growth or decay. So on all these, there's growth and decay. Since this one is going to be a decay, because it's radioactive half-life, it is decaying to that, right?
What if the decay just be half? We already know it's a half-life.
It's a half-life, which means that I have that much left. So in the graph would be like this. So I have a half-life, which would be right about here in this model, which would be half of it left of what I have. But then we're not looking for that. We're looking for, because we know this value and this value right here. And so we're looking for right here, 20%. That's what we're looking for. Look at the time at 20%. And that's why I needed to find a K first. All right, so I have the K value. Now, this is going directly into the next one because all I did is the half-life formula to get the K. Now, let's look at the problem that we have. 20%. Okay, how much is now left? 20%, right? How would I write that as a fraction? 1/5, very good. So it'd be 1/5. So it's 1/5 what? A, very good, right? 1/5 A, because that's how much I have left, equals A sub naught, right? And then E K T. Now, let's read the problem over again. What are we looking for here? I'm looking for the time. How long ago did the animal die? So I'm looking for the time. So that means that I have a K value that I could plug in there, and I'm not ready to go ahead and plug that in yet. So I'm going to call this right here my K, because the ln1 is 0. All right, so divide both sides by A sub naught. So I should get 1/5 is equal to E K T. Yep, ln 1/5. And then what do we know about that ln 1/5? ln 1 minus ln 5 is equal to K T. Divide both sides by K. And what can I get? Negative, negative makes that a positive, so it's going to be 5730 ln 5 over ln of 2. Okay. So, how old is this creature? How long ago did it die? 13,304 years ago. And this is approximation. There is a big plus or minus on this. Okay, because due to environment, it does change, but it's pretty consistent. So it could be, with 13,000 years ago, that's probably like a plus or minus, 200 or something like that. So, but there is a time window for those. All right. Uninhibited growth and decay. Amount of Y years grows without bounds or decays to 0. That's important. So decay can't go to negative, so it's going to go to 0. Many situations, there are upper value m, which is going to be my maximum amount that the y cannot exceed. Inhibited growth, that's what we're talking about, population, because it is inhibited. I can't go, to a certain point. So our population of the world it is inhibited by the amount of resources we have. Okay, where the lower m value cannot go below inhibited decay, inhibited growth decay model change rate restricted time satisfies differential equation. So if it's going down, it's decay, it should decay down towards 0 if I'm going to a certain point. Okay, here is the inhibited growth model. Now, if you're looking right here, it is with the derivative, okay, the change in y over the change in t, and it should be my maximum, okay, some rate minus whatever my initial is, okay, times k is going to give me the rate of change to that, where y is going to be less than my maximum value. So I should have some value because this is a growth model, okay, and now in a decay model, which is slightly different, y is more than my maximum because it's actually starting here and going down. So same thing here, so it goes backwards on that one. So we know that the rate of change is going to give me some values that are right there. Now, do you need to actually be able to do this with these right here? No, these are part of the models to go along with it. Here is one right here that actually has a maximum. This is a inhibited growth. So if we said, I don't know, what do they say now? Scientific say what the population of the world should, what's the maximum population of the world? Because right now we're at like 9 billion right now, and they, like 20 years ago when we were actually doing these math problems and talking about this at school, and we're like, oh wow, 9 billion, our world's gonna fall apart when we get that many. I think it should be somewhere up there, like 10, 12 billion or something like that. They say is the population maximum. Are you looking it up, Victor? Thanos? Okay. $12 billion? Yeah. So they're saying that this is about 12 billion. All right, and right here, in that right there, for this, okay, this is important, especially if we're talking about that zombie apocalypse. So for this, the population would go down to 0, but there is a number where the population should balance out. It should not go below that number, otherwise our population would die out. So for this line to keep going, there is actually a number. I think it's like 10,000 or something like that, where for like any population, because when they're talking about colonizing other worlds, I think it's 10,000 is the number to keep the gene pool, available for, instead of just the shallow end. Anyway. All right, Newton's law of cooling.
How many days is this lesson? Just 1 day?
Yeah, 1 day. We only have the AP questions for homework.
Oh, sure.
Yeah. All right. Newton's law of cooling right there. Now, what's the word cooling mean? Is something going down or is it going up?
Going down.
Okay, so that means that my U of t, which is actually going to be my temperature that I'm starting off with, it should be going down, right? So the rate of change is equal to U of t minus t. Now, going through here, where t, suppose object heated to a temperature of U of t, that's my starting temperature. So U sub naught, and then time t0, The object is put into a medium with a constant lower temperature, causing the object to cool. So there was an AP question that actually had to do with they microwave a potato, and then they set the potato down in the regular room. Okay, so right here, with a constant lower temperature, Newton's law of cooling states that the rate of change of the temperature of the object with respect to time is continuous proportional to the difference between the temperature of the object and the ambient temperature, okay, the temperature of the surrounding medium. That is, if U is equal to U of T, the temperature of the object at time T, and if capital T is the constant, okay, ambient temperature, that's important, room temperature, and this is my heated temperature, whatever my starting heated temperature should be. Okay, where we at? Constant ambient temperature, then the Newton's law of cooling is modeled by the differential equation here. So, if we have these values here, what can we find? We can find the K, can't we? Yeah, and that's important. So we can go through and actually do the math like we did a minute ago to actually find that K value. So here it is. Now, I wrote down all of this here. Now, it's on your thing. I copied this word for word so you guys could actually see all the steps to get to this. Where, okay, find the function by solving the differential equation, rewrite it in this to integrate both sides, getting to that point, find C, okay, initial right here, using expression C we obtain all the way down here. U of T. U of T means the temperature at a certain time is equal to my initial temperature minus my ambient temperature times e to the kt, which whatever my rate of change is after a certain amount of time, plus the ambient temperature. Now, did you guys, writing those down as like what they are is kind of important. So capital T is ambient temperature. That's the room temperature. U sub naught is my initial temperature right there. U of T is the temperature after a certain amount of time. And you guys know the K and T, right? K is the growth or decay, and in this one it's going to be a decay type model, and T is going to be whatever time it's looking for. All right, are we good?
So we just have to memorize these formulas?
It's the same thing. So when you see this problem on the AP today, or even on the AP when we do the practice exam, I'm going to make sure you guys have the potato problem.
Will they be different variables or just like the same?
No, that's the formula right there. That's the formula. You just need to know how to actually put it together. So it's specific to saying Newton's law of cooling. They might even give you this in the thing, Newton's law of cooling. I think they did when we actually had it on the AP. Said, oh yeah, Newton's law of cooling is this.
So is this whole thing just how you get that?
Yes. Alrighty. So that's it. Your homework is all AP. It's going to be due Friday.
Can I go for like traffic count?
Oh, from where?
Native American.
Oh, okay. So we're almost out of class here, so you gotta wait a little bit. Okay. All right. Make sure you like, share, and subscribe.